Good afternoon, everyone. My name is Dan Hu. I'm an assistant professor in mechanical engineering from Coventry University. So I have been here for 80 years. So mainly I just teach solid mechanics and stress and dynamics. But my research interest is actually in biomechanics. So I did some postdoc in University of Manchester and conducted some research about human body biomechanics, mainly in the human walking related biomechanics. The purpose of doing so is to could help develop some human related techniques such as assistive techniques or rehabilitation techniques. It's a it hopes that we can have some future application in the healthcare area, and of course could relate to the robotics area as well. So I'm going to present one of my research work about Xiegong Clogs study, and I hope you find it interesting and inspiring. And I would welcome you to have a discussion with me if you are interested. Today, the topics I'm going to present is when history meets biomechanics, the slope walking performance of ancient Xiegong clogs. So how do we think of this project to conduct the research is actually from some conversation I had with my former colleagues, as I mentioned in the beginning, Professor Pan from University of Waterloo. We had a bit chat one day, and one idea came up because we both studied in China, and we were so familiar with the history in China. And there was a very famous poet called Li Bai who lived in Tang Dynasty, and every Chinese know him. So we remember one of his poem called Tianmu Mountain Ascended in a Dream. There are lines in this poem called I put on his pegged boots and climb a ladder of blue cloud. Well, in Chinese, if there any Chinese in here, we say 脚着谢公鸡，身登青云梯. So here, his pegged boots indicate Xiegong's clogs. So who is Xiegong? Xiegong is also known as Duke of Xie. So his full name is Xie Lingyun, who was also a famous poet, lived in northern and southern dynasty China. To be specific, he lived between AD 385 to AD 433 period in Chinese history. So what's the speciality of his pegs boots or pegged shoes is there are two pegs under the shoe sole. When walking on uphill, the front peg will be removed. While walking downhill, the rear peg would be removed. So when walking on hills, it will be like you are walking on one peg shoes. And according to the historic record, these type of clogs could make the mountain hiking easier and more pleasant. So we were curious why these types of clogs would make walking on the mountains more easier and pleasant. So we had some questions turning up in our brain. Oh, what did the ancient shoes look like? So what materials were they made of? And how did people wearing these clogs? Do these clogs really improve walking efficiency on the slopes? And would it offer any help to the modern shoe design and the assistive technique design? So carrying those questions, we pre-designed our research project we aim to explore the relevant record of these clogs and reconstruct them. And then we aim to investigate the physiological and biomechanical effects while wearing Xiegong clogs. Based on those results, we will compare the 1-peg and 2-peg Xiegong clogs on uphill and downhill walking. Then we also want to explore some potential application in the shoe design and assistive technology that could enhance the walking mobility, safety, and the user experience. So that's how we designed our study. We searched for historic record for clogs dated back from AD 385 to AD 433. And this is the period of time Xie Lingyun has lived. We found some historic record, then we reconstructed the clogs according to some unearthed archaeological finds. Then we used some simulation technique to predict some biomechanical effects on the human body while wearing two different types of clogs. To validate those simulation results, we conducted an experiment with human subjects. We also explored some potential application of the Xiegong clogs in modern footwear through some student projects. So here you can see some examples of the unearthed clogs. So we found a literature reporting an examination of wooden clogs unearthed at the Nanjing Pigment Lane site from the Eastern Jin and the Southern Dynasty. And this was published in Chinese Cultural Relics. So in this publication, they claim they have found 12 pairs of clogs. And those 12 pairs of clogs can be classified into two types, type A and type B. So I have selected the two examples from each type of clogs. Type A clogs, the examples I show here are both made of Chinese zircover material. And Chinese zircover material is highly valued and very dense and hard wood, and it has beautiful wood grain. So it's very suitable for making shoes. If you look at those clogs carefully, you can see there are two pegs under the sole for type A clogs. And there are also 3 holes in the sole. And these 3 holes are for the shoelaces or shoe thread to come through and tie the clogs to the foot. So type B clogs are different from type A, as it doesn't have any pegs. So it's one piece, and there's a hole. You can see there's a hole in the sole for type B clog. And the type B clog, for example, type BG7 example I chose, is also made of Chinese zircover wood material. The same as type A. But type BG6, the lower one, is made of a different material called castornopsis wood. So this is another type of hardwood, which was commonly seen in southern China, and it has attractive patterns as well. So it was good for making shoes. There are also, you can see there are 3 holes in those clogs, type B clogs, where for the shoe laces or thread to come through and to tie them to the human's foot. So we selected the type A clogs as our example or benchmark. That is because the type A clogs has 2 pegs, and these pegs are connected to the sole through called tenon joint. So it can be removed if it's needed. So we found the dimension of this type A clog from the literature, and we adjusted the size to a man size 8, US man size 8 shoe size. I think it's equivalent to UK man size 7. We also did some modification to the shoe to the clogs. If you see the left original clogs, unearthed clogs size, the front and the back edge to the peg distance is not symmetric. And the front is shorter, the back is longer. But we made them symmetric. So the front to the peg equals to the back edge to the peg position, both 76. The reason of doing so is we want to create some slope angle when we remove one peg. So in this case, the both angles will be the same for uphill and downhill. For either we remove front peg or back peg, it will be the same. So we manufactured a few pairs, several pairs of these clogs. We used cheap wood. We couldn't afford very high-valued wood like oak wood, so we only used pine wood. But it worked, although it's not as hard as oak wood. We made several sizes from size 4 to size 9. So make sure that all the subjects who have attended the lab in a later stage, those clogs could be fit for them. All the holes you can see from the clogs we made, the 3 positions are exactly the same as we found. We actually followed the unearthed clogs, so they are similar positions, but has been proportionally adjusted because of the different shoe sizes. Before we conduct any experiment on those clogs, we decided to work on some simulation first. We want to know what simulation results will be like. So we created a defined a 3-layer optimization framework. So this framework can output muscle activations from only 3 inputs. And these 3 inputs are average walking velocity of the subject, human subject, the stride time, that is the time used to complete one cycle, complete cycle, and the double stance time. So that means when the double feet are standing on the ground, what's the time of that? The reason we want to conduct the simulation is we want to predict which muscles function would be influenced by the clogs first by simulation, and in order to find the fundamental reasons that make the walking on heels easier. We hope we could find some solutions from the simulation first. So now I want to explain what 3 layers optimization are. So first, this is the first layer optimization. So this is based on one of my work that is published in 2022. So this is the most outside or most fundamental optimization that it uses 3 inputs to output the kinematic and the kinetic information. The kinetic, so this model is, so this optimization is based on some inverse dynamics of human body, and for the objective of minimizing the time integral of the joint torque of all the joints, and subject to some constraints. So there are several constraints we have considered here, such as joint motion constraint. For example, for the knee joint, we want it to have positive flexion. So that means you can't bend your knee, that is the other way, that negatively. We also have some segment motion constraint. So that means there is a motion limit for the segment that it can move in the space. And some kinematics constraints, such as this ground contact with the floor, for example, the foot contact with the ground. So the foot must be above the ground when during the swing phase, and it must be contacting on the ground when during the stance phase. And task constraints, such as it must complete one stride length after a complete cycle, and also last the foot must follow this show rollover shape. So it's kind of another kinematic constraint. So this model can output kinematics in terms of joint rotation angles, the time history of it, and the kinematic and kinetic data, that is ground reaction force and joint reaction moments. They all in a time history format. So the first layer of optimization, the output from it will feed to the second layer optimization. Do I go next? Okay. For the second layer optimization. So second layer optimization is try to predict the muscle forces. So how can we get muscle forces? So we know that for human body, let's take a lower limb as an example. There are joints in the lower limb, and at each joint there are muscle forces, muscles around the joint, which create the forces to move the segment. Actually, for each joint, there are more than one muscles, more than one muscle or more than two muscles. The minimum we need is one flexor, one extensor. So that means two muscles will be enough to activate a joint. But in reality, we have more muscles. We could have 3, 4, even 5 muscles around one joint. So the remaining muscles, except flexor extensor, the remaining will be redundant. So how do we process this kind of redundancies in human body? So our central nerve system actually knows how to do it. It's kind of force the system to follow a most efficient way. So that's why we consider that muscle efficiency or minimal energy cost as a optimal criterion for the muscles forces distribution around the joint. So it's a energy cost, it's an energy based, or it's a fatigue, we call it fatigue based criterion. So the second layer of the optimization is try to predict these muscle forces at each joint based on the optimal optimal criterion of minimal muscle fatigue and subject to some constraint. And this constraint will be muscle forces can only provide some pulling force to the joint. So that means the muscle cannot sustain compression. So that means you can't compress the muscles. The muscle can only provide pulling force. So this is a constraint. So from the second layer optimization, we achieved some muscle forces, and this will be used to predict muscle activations. In theory, we can calculate muscle activations from muscle force straight away based on some muscle models. However, due to its complexity of the muscle models, here we used Hill's model, it has very complex expression in formulas. So we decided to use another optimization, try to match the muscle forces we calculated from or predicted from second layer, and to with the calculated muscle force from Hill's model. Then we can minimize the errors between these two, and subject to some constraint like activation level must be between 0 and 1. So that means 0 and 100%. And in this way, we can predict the muscle activation level A. And this muscle activation then can be validated against the EMG data in the later stage. So which is another way to tell whether this simulation would work or not. So here I want to present some simulation results from, this is from the first layer of the optimization, which is mainly kinematics and of course some kinetics. So here you can see this is a simulated two-dimensional in sagittal plane walking gait simulation. The above one, the top one is for 2 pegs walking, and the lower one is for 1 peg walking. Also, we achieved some simulation results for downhill walking. And from the simulation results, we can see for uphill walking, if you see clearly that you can notice some difference between the 2 peg and the 1 peg walking gait, especially for the foot rotation. So for stance phase, the 2 peg actually is having more dorsiflexion than the 1 peg shoes at the stance phase. And if you notice, if you have noticed that the lifting of the foot off the ground for 2 peg is faster and harder than the 1 peg. So this indicates that 2 peg walking may involve more muscle forces at the ankle position to lift the foot off the ground for the 2 pegs walking. For downhill walking, that the foot is for 2 pegs, it at stance phase, it's involving more plantar flexion, if you have seen. So this would further influence these muscles around the ankle joint and probably the muscle around knee joint as well. So second layer optimization output the muscle forces. So here you can see I have considered 8 muscles in the optimization frame. These 8 muscles are Gmax, which we call it gluteus maximus is some muscle's name, which in your back of the hip position. And IL muscle, I'm not going to tell all the long name of it, but if you're interested, you can Google all of them. And the hamstring force, GAS is gastrocnemius, SOL is soleus, and RF muscle is rectus femoris, VAS muscle, and TA muscle. So these muscles, they have their functions. They are providing either flexor or extensor function to each joint. For hip joint, the Gmax and the HAMM provide the hip extension, and IL, RF provide the flexor for the flexor function for the hip. For for the knee joint, VAS and RF provide the knee extension function, while a hamstring and GAS is act like the knee flexor. For the ankle, SOL and GAS is ankle dorsiflexion or plantar flexion, sorry, and the TA is a dorsiflexion muscle. So from the results, we can tell that out of those, within those 8 muscles, 3 muscles peak has been reduced for one peg walking condition. Similar pattern or similar trend for the muscle forces have been spotted for the muscle activation as well. For downhill walking, within 8 muscles, 5 muscles have been found that the peak has been reduced for one peg walking, and their activation level as well. So in summary, the simulation results tell us this for uphill walking, the muscles around ankle joint, for example, soleus, gastrocnemius, and TA muscle, their peaks has been reduced while walking uphill with the one peg clogs comparing 2 pegs. For downhill walking, muscles around knee joint and the ankle joint, like hamstring, RF, VAS, Gmax, TA muscles, their peaks have been reduced while walking with one peg clogs comparing to 2 pegs clogs. To validate those simulation results, we designed some experiment, and thanks to the Center for Physical Activity, Sport and Exercise Science, PACES, from Coventry University, we were able to use their facilities. And this experiment has been approved by some ethics committee from Coventry University, and all the participants have been informed consent before participating. We recruited 8 healthy subjects, 6 male and 2 females, and age range 33 plus and minus 8 years, and mass is 76 minus plus 10.5 kg. The height is 172 minus and plus 9.8 centimeters. So the experiment conditions is mainly for comparison between one peg vs 2 pegs walking on different slopes. So the slope angle range has covered from downhill 25% to uphill 20%. We selected 3 km per hour for uphill walking and 2.5 km per hour for downhill walking. This is a walking speed we selected. And each subject has walked for 5 minutes for each trial. So what data have we collected? So we collected some physiological data. So that is oxygen uptake and carbon dioxide output measured by metalyzer system. And this data can be used to calculate the metabolic rate. We also collected some surface electromyography data, that's EMG data, muscle activation data. We used some trigonal analysis system. Our subjects worked on the zebra's treadmill, and this treadmill is has instrumented sensors and cameras. So we were able to record the video of subjects walking on the treadmill. Of course, it can only capture the sagittal plane motion. The treadmill recorded some data and some spatial temporal data, such as parameters such as the stride length, stride time, stance time, etc. And the ground reaction forces were also be collected by the treadmill system. So here are some results presenting. The metabolic cost showing that there's some difference between one peg and two peg walking. So we can see, in general, uphill walking consume more energy than downhill walking, which makes sense. For steep angles, slope angles, such as 20% for uphill walking and 25% for downhill walking, we notice one peg, which is deeper color, metabolic rate is lower than two peg metabolic rate. And this is consistent between uphill and downhill. For downhill walking, all the conditions shows that one peg is consuming less metabolic rate and is consuming less energy. But for uphill, this difference or this advantage of the one pegs was not very obvious for moderate slope angles. Even for 10% slope angle, we notice the two peg seems saving energy than using less energy than the one peg. We reckon it's possible because the shoe angle is around 15 degree, which is higher than the slope angles, and probably this contribute to the energy difference for a very low slope angle walking. This is EMG data results. So we collected the EMG data for all 8 muscles in lower limb to match with the simulation. So we found for uphill walking, those 4 muscle forces have been reduced for one peg walking. And from the figures you can see, solar GAS, T and Gmax muscles, their peaks are increasing with the increment of the slope angle. So this is 10%, then increase to 15%, 20%. So this makes sense. And the peak, you can see the solid line is for one peg one peg clogs walking, and the dashed line is for the two pegs. So we can see that the solid line peak is lower than the dashed line peg, so which means the one peg clogs walking is actually reducing the maximum muscle activation through the time history. And these are the results for the EMG results for the downhill walking. And within the 8 muscles, we found 3 muscles peak have been reduced for one peg walking. Again, we noticed this increment trend for the slope increment, but always this solid line is below this dashed line at peak position. All the results for uphill and downhill, they are all normalized by the lowest slope condition. So you can see the first one, the peak will be 1. Same for the uphill. So all others is normalized by this 10% and 15%. Anyway, so If we compare the simulation results and the experiment results, we find some similarity and some difference. The simulation for uphill walking, uh, three muscles show the same trend as one peg. Pegs have been reduced, but one muscle force was not picked up by the simulation, that is Gmax. For downhill walking, we noticed the simulation seems predict more muscles than the experiment. Their peaks have been reduced for one peg. We reckon this could be that the predictive model is a very simplified model. It's based on a two-dimensional sagittal plane linkage model. So it could not fully represent it or reflect the actual case of the human walking gait. So this may contribute to this difference to the experiment data. We also compared the simulation results in activation with the experiment activation EMG data. So here we used soleus as an example to show whether they match. And we find that in general, the trend is matching. That means in time history, seems it is showing similar peaking timing position. And most importantly, that we find the one peg soleus activation level is reduced for comparing to peg. And this has been shown in both experiments and simulation results. So after achieved so many results, we can say that the one peg clogs design can enhance the neuromuscular efficiency by improving coordination and reducing muscular contraction on both uphill and downhill. They can also improve energy economy by lowering the metabolic cost during slope locomotion. The reason behind this may be due to the altered foot-ground interaction affecting contact mechanics and plantar pressure distribution. And this likely redistributed mechanical load across the lower limb, and which may influence the joint movements and muscle activation patterns. These research findings support the historic claims regarding the function of the value of the design. They also show that the Asian design can be functionally optimized. So that means maybe when the people in many years ago in northern and southern dynasty, they probably have considered design some clogs and trying to make the best design or as good design as possible. So we can see behind those clogs design, there are some evidence that we can support this. The results have also brought some implication that it can be used for footwear design, rehabilitation, assistive devices, and probably for some outdoor performance benefit that as well. So we did explore some potential application of the Xiegong clogs in modern shoe designs. We reckon it would be too complex to design a brand new shoe. So design outsole for shoe is a good idea. So here I present two design ideas from my project students. So first design used this ice snow gripper, which you can easily buy from Amazon. Then the student designed two POA, 3D printed POA blocks. And on the blocks, there are some rubber material to provide some grip or friction. These two blocks are different in height. So when walking uphill, the higher higher block will be attached to the rear position. And when walking downhill, they will swap the position of these two blocks. So students actually had a trial walking on wearing them and walking on some slope. And they said, feel all right. Well, we couldn't collect any experiment data due to the ethics approval issues. So we can only do try and fit. A second design is a block, which is also 3D printed. So it has an elastic strap and can connect the block to the shoe. So it has some outstanding piece on the back of the shoe of the block to stop sliding, the shoe sliding, and they also added some rubber material under this block to provide more grip on the ground. The student also further developed this model by adding some this detachable slide under this block. So this lower bit can be removed or sliding to adjust the for the purpose of adjust the height of the pegs or these blocks. So the original idea was to design some adjustable, height adjustable the outsole for the shoe. Although it's not perfect, but seems working or seems reflecting the idea. Of course, this research has some limitations. It's limited by a small sample size. We only had 8 subjects, and it's based on short-term testing conditions. We did not assess whether equivalent one-peg trainers would be more efficient than conventional trainers. So in the future, we would want to investigate larger sample and the long-term adaptation effects. We would want to continue to work on the application of the Xiegong Clogs to modern footwear design. In conclusion, this study tells that one-peg designs can reduce metabolic cost and muscle activation. And we find that integration of simulation and experimental approach provide a robust analytical framework. And this work has translated ancient innovation into a modern biomechanical insight. We proposed some concepts of designs show that there is potential application of the Xiegong Clogs in modern footwear design. I would like to acknowledge the contribution of all collaborators, including the staff from School of Engineering of Coventry University, who kindly to support this research by being part of my subjects, and technical support provided by Lee Bolt of PACES Research Center, as well as some guidance and expertise from Professor Jason and Professor Zhao Pan from University of Waterloo, Canada. And as I mentioned in the beginning, Professor Pan, who was the researcher, we had this idea at the first place. And his student also helped with this research at the first stage. And thank you so much for your attention, and I welcome any questions and discussions.